All right, now we're on to some mechanics free response. So before we get started, my objective for this form, because it's the first one, is just to get a sense of the style. So I purposely did not write overly novel or difficult scenarios here. So I imagine my cut scores would be pretty high on this. I imagine that the 5 cut on this free response is probably near 90%, just based on kind of my own thoughts. But of course, I'll keep the description updated with that, because this is sort of learning the format and understanding the types of things we ask and the skills we look for. So question 1 is mathematical reasoning. This is usually what can be the hardest one because it's mostly symbol math with one picture thrown in there. So we have a classic looking static equilibrium problem where we have a beam attached to a wall and there's also a cable there. So we're given the mass of the beam, it's uniformly distributed, and we have an angle theta. So first of all, sometimes you begin with a picture, sometimes you end with the picture. And if you start with the picture, it's intended to help you with your derivation. So a good strategy for all the questions is to read all 4 parts before you actually do them. I say 4 parts because the TBR can have up to 4, but this is our mathematical reasoning. So it's split into a large derivation, which is A, and then a mini derivation, which is usually unrelated, and that's B. So we have an extended body diagram here. Then we're going to be trying to find the tension force that the cable exerts on the beam. And then we're told that we cut the cable and want to know something about the beam's acceleration. In part B, we see there's just something different happening. So it definitely seems that the intention here is that our force diagram should help our derivation. So let's do that. This is called an extended body diagram because the point that you draw the forces matters. It's not a dot, it's a physical object. It's a rigid body. So of course, this is a beam with mass. So it should have gravitational force, its weight. It's going to pull directly down as per usual. You can label that however you want. I'll use F notation, so I'll call it FG. Any reasonable description of weight is fine. And then also the more clear one to get here is going to be tension, right? Because we definitely have a force that's pulling that beam. So that would be a reasonably labeled tension force. And this is where a lot of people stop, but it's actually not full points. Because remember, this beam is in equilibrium. If I look at my diagram, there's no way this beam can be in equilibrium because the tension force is pulling it up and left. So there must be some other force that keeps it in equilibrium. And if you remember, what often happens with these static equilibrium problems is your object is connected to something. And whenever you're connected to something, you get a contact force or a normal force. So the pivot point itself is going to exert some force. Maybe I'll try to at least balance the components there. And you can call this whatever you want. I'm going to call it a normal force. Sometimes it's called a hinge force or a force from the wall, anything like that. So how did I award points for this? Well, the MR diagram is only worth 2. So the easy point you get just by a downward gravitational force at the middle. Of course, we are quite generous as what is meant by middle. And then for the second point, you have to get everything else correct. So we have Ft is up and to the left. And you need a normal force with a rightward component. Because it's not necessarily clear without doing any math what the vertical component of this needs to be. You could get it actually in either direction depending on what parameters are given. So we're not assuming you've done any math. Oh, there's not a third point. You need both of these. You need the normal force with some sort of rightward component. So you get 2 points on part 1 for your diagram. You just need both of the forces correct. So you could have just as easily drawn a horizontal normal force or a downright normal force. All of those would have helped on your quest to get A2. And of course, the positions of these have to be relatively correct. All right, now let's do our derivation. So derive an expression for the tension force exerted on the beam by the cable. Well, if we look at our free body diagram, we see that there's a tension force, which we don't know, but we would like to know. We have a gravitational force, which is of course mg, and then we have this mysterious normal force with a wall. And the key with these torque problems is that since torque depends on your perpendicular distance from the pivot, a clever strategy is to pick your pivot point to be the place where you have a force that you're trying to get rid of. So I don't know tension force, but I shouldn't pick the pivot to be here because that gets rid of the force I want to calculate. So I should actually pick my pivot point to be the pivot in the problem, and there's no coincidence I use that language there to try to get you thinking about that. So I'm going to sum my torques about the pivot point. So I'm just going to start by saying, yeah, this beam is in equilibrium. So there must be no net torque about any point that I pick, but choosing the pivot on the left end is probably the smartest choice. And why is that? Well, if I redraw, what I have, we know that we are going to have a gravitational force, mg, that is attempting to rotate the pivot clockwise this way. So mg is trying to do that. Now, we also must have some sort of force that's trying to twist it the other way. And of course, we know that's going to come from tension. So our tension force is at least going to partially contribute to that torque in the other direction. But more specifically, it's the vertical part of tension because it's about perpendicular. So we're looking at the component of the force that's perpendicular, which in this case, it's not actually the full tension force. It's going to be the sine component or the vertical component. So why is that true? Well, again, if we look at our picture, we see that this sort of horizontal component of the tension, that's not doing anything to try to rotate the beam. All of the rotation is coming from the vertical component. And we are given the cable angle as theta, so we can just say that that's ft sine theta. So now it's just a matter of equating torques. So we can say that the torque from mg is equal to the torque from the tension force. And torque is again r perpendicular times f. Or in this case, I'm going to say r times f perpendicular, because we know the component of the force perpendicular. So all of mg is going to assist in rotating the beam. And mg is located directly at the center of the beam, so that's L over 2. And the tension force, it's ft sine theta that's helping us rotate, and that's located a full distance L along the beam. So now it just becomes a matter of simplification. Notice I didn't say L was allowed because it cancels. So goodbye to L. So we just get mg over 2 equals ft sine theta. So ft is equal to mg over 2 sine theta. So despite this, that it took us a minute to talk through, this is also only worth 2 points. So it was straightforward enough that you get an easier point, A3, just by some sort of net torque is 0 equilibrium argument. And it had to be multi-step. So if you're substituting things, even if it's totally wrong, you get A3. And then to get A4, you just have to get the answer correct. Not consistent, it has to be correct. So now we're on to the second part, which says the supporting cable is then cut, and the beam begins to rotate about the pivot. Given the rotational inertia of the beam about its center is 1/12 ml squared, derive an expression for the initial angular acceleration of the beam about the pivot in terms of L and physical constants. So actually only L should be our letter that's not a constant. So this means we cut the cable. So we have this picture now where there's no cable force, but we still have our mg pulling down at the center. and it says initial because if this beam starts to rotate this way, mg is not going to be perpendicular anymore, and we have to do some math there. But again, we're just cutting this cable. Okay. So if we want acceleration and we know things about torque, we're not going to use F equals ma which is translational. We're going to use net torque is equal to I alpha, Newton's second law for rotation. So the net torque, that's pretty straightforward, because the net torque, as we saw earlier, well, it's just due to gravity in this case, and that's just going to be mg, and it's located at L over 2. So we did get that expression last time. It's just now there's nothing to balance it. Okay. But we can't just substitute in this quantity for rotational inertia I, because that's actually giving us the rotational inertia about the center. And that's not the point it's rotating about. So anytime you're given sort of the wrong moment of inertia, that's telling you it's parallel axis theorem. So we also know that I is equal to I at the center of mass plus md squared, where d is the distance from the center. So we were given the center of mass rotational inertia, if that was our pivot, is 1/12 ml squared, and then d, well, how far away am I from the center of mass if I'm not pivoting at the center, but instead one of the ends? Well, that's just half the length. So that would be L over 2, all squared. And we can do some fraction arithmetic here, where this is going to be 1/12. So this is 1/12, and this is 1/4. And also 1/12 is the same thing as, 1/4 is the same thing as 3/12. So we actually end up with 3/12 plus 1/12, which is 4/12, which is 1/3. Now, actually, this could be a result you may have stored in your brain for some reason. You may actually have known this fact, that a rod about its endpoint is that 1/3, but there was no assumption you knew that. So now it's just plug and chug time, right? Because we have torque and we have moment of inertia. So our torque, mg L over 2. Our moment of inertia, 1/3 ml squared times alpha. Goodbye to the mass. Goodbye to one of the L's. So if we do that, we would get g over 2 equals alpha L over 3. So that means that alpha is equal to 3/2 times g over L. And notice that the only variable there is L, because g is a constant. So how do we get our points here? Well, we're more stingy on this part. So to get A5, you had to get the correct torque. So you had to indicate the net torque was mgl over 2. You had to indicate the moment of inertia was 1/3 ml squared. And then you had to get the correct answer for A7. Not consistent, it had to be correct. Because we're assessing different things. This was assessing torque, this was assessing parallel axis theorem, and this was assessing Newton's second law. So we sort of needed the correct answer. So no partial. It would be hard to get A7 without 5 and 6. So when you're done with this part of the MR, it's going to transition. Now, a really well-written MR should have a part B that doesn't need you to know anything in A. So I always keep my MR part Bs sort of on a little island. So here we have a different beam of length L, showing you this is something different happening. It has a non-uniform mass density that varies according to a lambda function. And we want the x-coordinate of the center of mass, given it lives in this coordinate system here. Well, of course, center of mass, there's really only one formula for center of mass, and it says x center of mass would be equal to 1 over the total mass times the integral of x dm. And once again, we're actually only allowed to use L. So it's a different beam. So I can't just say this is like capital M. I can't say that. So let's figure out what M total is first. So remember that by definition, this quantity lambda is defined as the amount of mass you gain per small length. So it's the extra mass you get for a little extra length. It's mass per length. So this means that the extra mass you get is equal to lambda times the length. So if I wanted the total mass, all I'd have to do is I'd integrate all the little dm's, which means that I integrate lambda dx over the given interval. And we do have that interval, right? We know we're going from 0 to L, and we also know that we know what our lambda function is. So I integrate from 0 to L. Lambda was cx cubed. And we're just integrating that with respect to x. This is just a classic power rule, right? We get 1/4 cx to the 4th from 0 to L, which gives us cl to the 4th over 4. And that's just the total mass. This actually isn't what the question wanted us to do. The question wanted us to actually find the center of mass coordinate. Okay. Well, now we can just plug in. So x of the center of mass is defined as 1 over m total. So what is m total? M total is this quantity. And then it says integrate x dm. So I plugged in here for my total mass, and now I just need to plug in for x dm. But remember we said dm is lambda dx. So I can just do my same integral as last time, except now I have an extra factor of x. Because we said that dm is lambda dx. So if we do that, I'll simplify this sort of compound fraction. So I get 4 over cl to the 4th times the integral from 0 to L of cx to the 4th dx, right? Because I picked up an extra x. And that's going to take out the c. That's going to take out the c, because that lives in the numerator and the denominator. So I get 4 over L to the 4th times x to the 5th over 5, evaluated from 0 to L. And that's just going to be 4L to the 5th over 5L to the 4th. All the L's cancel but 1, so we get 4/5 times L. Notice that is a very clean answer just in terms of L. So the part B derivation can definitely take some time, but it's only worth 3 points. So you got a point for making it multi-step. So if you did sort of center of mass related items and tried plugging stuff in, you get B1. And even if you didn't, you actually get a point, I said, if you use dm as lambda dx. That gets you a point too. Now to get B2, you had to integrate the mass density correctly to get the total mass. And then to get B3, you of course had the correct final answer. So those are your 3 points there. So this is where it gets hard. Like, I tried to balance kind of the routineness of the first part with a more multi-step calculation, where it's not often you have to actually integrate for m total and do the integral like that. Usually it'll just give you the lambda and you just go. So I thought that was a pretty standard question, but again, I will always argue that question 1 is probably the hardest. All right, now onto the TBR. So the TBR, translation between representations, has sort of a different approach than the MR. So it gives you a lot of time, and it's actually worth the most points. It's worth 12, but it tests the most skills. It asks us to do quite a few unique things. So TBRs are really important. You read the whole thing first, because it can tell you a story about what the objective of the problem is. So a TBR isn't really telling a story in sequence, where do A, then B, then C. It's really doing the same problem in different ways and looking at it from different angles. So it's like telling different perspectives. So for most good TBRs, you can actually do parts A, B, and C kind of in any order. So we have a block that's placed on top of a movable ramp with mass 3m and height h. We release the block at t equals 0, and at t equals 1, it leaves the slab. And we're given that there's no friction to keep everything nice and clean. So we do know that there's going to be these different topics in the FRQ. Usually we're given at least one rotation, so we probably knocked that one out of the way first. And this is definitely some sort of conservation question because we have things that are going down a ramp. It's pretty clearly some sort of energy thing. But actually, it might subvert your expectations at first because part A says draw bars representing the x component of the momentum. So actually, it looks like this is a conservation of momentum question. So that's that. Part B wants us to derive an expression for the speed at the bottom of the slab. Wants the speed of the slab at that time, so not actually the block, but the moving slab. Part C wants us to graph the velocity of each object as a function of time, just during their sort of descent. And then part D, it's the classic, do parts A and C agree with each other? So we get the agreement variation of the TBR first. All right, so let's start with momentum. So momentum, of course, we have the formula that momentum is defined as mass times velocity. And all of this looks to be taking place in this horizontal coordinate system. So we're just doing this sort of x. Well, at t equals 0, everybody is at rest. So if everybody's at rest, neither the block nor the slab have any momentum. So now let's think about what's going to happen at t equals t1. So at t equals t1, we essentially have this scenario where we have the slab, and then the block has left it. Well, remember that conservation of momentum tells us that the total momentum of the system must remain constant. So that tells us that any momentum that is gained in the plus x direction from the block must be balanced out by some sort of leftward momentum in the other direction by the slab. So we know that these objects are going to be moving apart from each other once the block has left the slab. So what that allows us to do is we can now know that I don't really care what's happening with their actual magnitudes. I just know that the block must be gaining some momentum in the x direction, and the slab must be gaining an equal amount of momentum in the minus x direction so that we get this cancellation to happen. So how did I grade the bar chart? Well, B1 is pretty straightforward. You need this picture. You actually can't leave it blank. You do have to indicate that there's 0 by writing something. So to get B2, you had to say that the block has positive momentum and the slab has negative momentum. Because we're looking at the x component, and I did actually define what the x direction is, the positive direction, so you do have to have the block be the positive one. And then for B3, it doesn't matter what happened, but you have to conserve the total momentum of the system. So this just means the total bars, if you add them between your before and after charts, they have to match. So that means that I have 0 plus 0 equals 0 bars here, and I have 1, 2, 3, -1, -2, -3, so my sum is 0 in both. It doesn't have to be a correct sum. You just have to make sure that the total hasn't changed. So your momentum accounting needs to work out. All right, so now we want to find the speed of the slab at T1 in terms of H only, basically. Well, if we look at what's happening here, this is definitely a conservation of momentum type question, but also we have a height h, so it's an energy question. So you can actually tackle the two parts in any order because we're actually going to have to conserve both. So I might start by saying, I might start by using energy, and we'll see why we need momentum. Now, if you go the other way, you'll see why you need energy. So I might say that what's happening here from an energy point of view? Well, from an energy point of view, I have only gravitational potential energy to begin, right? Because I have a crate that's above the ground. And then at the end, I have only kinetic energy because the block and the slab are both moving. So I can take my energy snapshots to say that the system potential energy at the start gets turned into kinetic energy at the end. But actually, we have to be a bit careful because it's not just one object, it's actually two objects that's sharing the momentum. The block and the slab both share the energy. So what is the U term? Well, the only thing that's losing height is the block. So that means my gravitational term is just going to be 1 mgh. And then for the block, its kinetic energy will be 1/2 mv squared for the block. And then I should actually match my letters. And then my kinetic energy for the slab is going to be 1/2 times the slab's mass times the slab's velocity squared. And I can't assume that these are the same, and we'll see why they can't be. So if we actually do this, we can simplify and we'll get some equation that looks like getting rid of the m's and multiplying by 2. We get 2gh equals the block's velocity squared plus 3 times the slab's velocity squared. So we can't solve this for the slab's velocity because we are missing the block's velocity. So we need some sort of relationship. And how do we get that? Well, of course, we're going to use our other equation, which is momentum. So that's why I had us do the bar chart so that we could see that we could say that the sum of the momentum is constant. So we could say that the momentum at the start, which was 0, is equal to the momentum at the end, which is the block momentum and the slab momentum. The block's momentum would be m times v of the block, and the slab's momentum would be 3m times the velocity of the slab. And you could have sort of just reasoned this in your head if you know about sort of explosion type problems, where notice this just says that v of the block is equal to 3 times v of the slab, just in the opposite direction. Which makes sense, right? Because if these both have to cancel their momenta to ensure that we have 0 net momentum, the block has to be moving at triple the speed to cancel the slab's momentum, because it has triple the mass. So now we just go on a plug and chug exercise. So we had 2gh equals the block velocity squared, which is 3 times the slab velocity, plus 3 times the slab velocity squared. So we get 2gh equals 9v of the slab squared plus 3v of the slab squared. So that turns to be 12. So we get 2gh equals 12v slab squared. So we get v of the slab would be, well, 2 over 12 is 1/6. So we would get square root of gh divided by 6. Kind of an interesting problem. So it's not computationally intense, but there's a couple of weird wrenches in this. I actually really like this problem. So where's your points? If you try to conserve something correctly, you get B1. If you write energy correctly, you get B2. Well, actually, I would say, yes, you'd get B2 from this. Although you can check my rubric. I think actually if you write this, I believe you would also get B2. I don't know if you need to have it substituted in or not. But the key with B2 is understanding that the slab and block each contribute to the kinetic. To get B3, you have to come up with the 3-to-1 relationship between the velocities. Of course, you could flip it the other way, and that's totally fine. You could say the slab is 1/3 of the block. You actually don't need to justify that. You can kind of just spawn that in. And then you get B4 with the correct answer. So I'd say there's some gettable points here, but there's also some harder ones. This is probably my hardest of the 4. All right, now we want to actually sketch the velocity of each block as a function of time. So let's do that. Well, what do we know about the block? Well, the block is going to be moving to the right, which is positive x, and it's also faster. How many times faster? 3. So we need a block, and there is actually grid lines here, meaning I can grade you on this. So the block, I'm going to have it go up 1, 2, 3, and that's actually all I need is that, and we can label that V of the block. And then the slab, what does the slab do? Well, the slab goes in the opposite direction, but it has a lower speed, exactly 1/3 of the speed, but in the opposite direction. So this actually earns you full credit for the graph, because how I awarded points is you get C1 by being linear with a y-intercept of 0 for both functions. If you only drew one, I guess you can get that point. For drawing only linear functions that begin at the origin gets you C1. For C2, you need V of the block to be positive at all times, or 0, and you need V of the slab to be strictly negative. And then for C3, you need to have V block at T1 has to be 3 times V of the slab at T1. So that's a tricky point. Now, if you wanted, since we said both surfaces are frictionless, you could totally just extend each of these like this. That also works, but we only graded from 0 to T1. So that's an interesting graph. And then indicate whether your graph in part C is consistent with your bars in part A. Briefly justify your answer by referencing functional dependence. Now, as someone who writes these, it's my opinion that point D2 is probably the hardest on the whole FRQ, except maybe the part D2 and the best fit line. So, first of all, I know, pick one, by the way. First of all, the fact that you're seeing this video knows the answer is consistent, because if not, I would have caught it. So there's your metagame there. You have to make your claim. So how do we justify it? Well, it says referencing functional dependence, which means you need a formula or proportionality. You can say many good things and not get point D2, because this means a very specific thing in physics. We have to state some sort of formula or power relationship. So what is graphed? We have velocity in part C, and we have momentum in part A. So we're asking, how could a velocity graph relate to momentum bar charts? Well, we know that momentum is equal to mass times velocity. So you did actually need to say this in some way. You could say momentum is proportional to mass and velocity. The key here is you need actually both. Why do you need both? Why are we saying you need both for D2? Well, in part A, I said the blocks have the same momentum as we saw in part A. They have to have the same momentum, those canceling momenta. So V of the slab must be less than V of the block, since M of the block is less than M of the slab. So anything like that gets you D2. So to get D2, it's 2 parts. You need to have some sort of P equals MV relationship. You have to say momentum depends on mass and velocity, because if not, we don't know the dependence. Now, the second part, you have to include this sort of inverse relationship, that the thing with bigger mass must have smaller velocity to create the same momentum. So that's why I think D2 will remain one of the hardest points. So you just say consistent or not consistent, you get D1. Of course, they actually need to be consistent. That's something your grader would know how to do. I had the pleasure of grading 2,000 of these TBRs last year. So we had a lot of interesting discussions on what this means. But I could say it's consistent because they had to make the same momentum They had to make the same momentum, but the masses were different. So if they have the same momenta, their velocities could not be the same. You would also say you would say not consistent if your graph was like flipped upside down or something. So it is actually kind of hard to earn this point. It's hard to grade this point if you're not super experienced with that. Of course, if you have any specific questions, you can let me know. So again, this is a pretty interesting one. I love the TBR. This is what good physics assessments look like. It's the TBR. Like, how are these different ways that you can come to success? So this is definitely the hardest of the 4 FRQs today. All right, now we have what I think is one of the easier ones of the day, especially this first part. We got the lab question. So don't think of the lab question as a question. Think of the lab question as 2 mini questions. So there's a cookie cutter, here's some meters, how do I measure the stuff, what do I graph, what do I do? And then there's the do-it-yourself best fit line Desmos plug-in chug fest. So in experiment 1, students are asked to use a linear graph to calculate the force constant of an ideal spring that hangs on a ring stand. The students have access to masses that can be attached to the spring as well as a ruler. Whatever could we possibly measure, right? We have masses and a ruler. So this is really kind of just the freshman physics version of this lab where you're calculating K. I didn't do anything crazy with this one. Indicate quantities that could be measured. So this is not write an experiment. This is saying what could be measured. We can say the hanging. We can measure the hanging mass M, and we can measure the spring extension delta X. Now, because of how Hooke's law works, you could have just said length. You could have just said length and this will work out because you'll just get an intercept. Yeah, you could just graph the length because if you don't subtract stuff with Hooke's law, you'd plot something that has a y-intercept of the initial length and the slope is still k, by the way. So this is how you get A1. Say mass and length of some sort. How do we reduce uncertainty? Well, it's how we always reduce uncertainty. We repeat for multiple values of M. Something like that. Measure multiple times, do repeated trials, other things, calibrate the force sensor, whatever. We don't have a force sensor, but you get the idea. Just say do multiple trials or like test various things. All right, what can be graphed to calculate K? Well, of course, this is a spring question, right? We know that the spring force has magnitude K delta X. But this is not a quantity we know. We did not have a force meter, so we can't say force versus delta X. We need to figure out what that force is. And well, it's pretty straightforward, right? Because we're just hanging a mass from a spring. So we know that there's going to be a gravitational force mg down, and then there's going to be a spring force k delta x up. So that means that our equation, we can just replace the spring force is equal in magnitude to the gravitational force. So we can say mg is equal to kx. And this is linear already. I can just put mg in a box, and I can put delta x in a box. So I can say graph mg versus delta x. Do not say and. You have to say versus, or if you want to be really clear, you can draw the axes. So any valid choice of this works, because if you just say graph blank and blank, well, actually, sorry, that's good. That does earn you B1. But it makes your slope relationship a bit ambiguous, because if you flip the axes, the slope would be reciprocated. So what's the relationship between K and one feature of the graph? Well, this is pretty straightforward, right? I have mg is equal to K times delta X. So my slope is equal to K. So let's talk about some alternate solutions real quick, because I'm sure there's several of them. A consistent analysis of your graph gets you P2. You don't have to solve for the slope if there's weird numbers in there. So I could have graphed m versus delta x. Like I could have came up with the equation m equals k divided by g times delta x. And you'd say your slope is k over g. That also works. So if you manipulate this, you just have to be consistent with what you wrote for B1. So you have a lot of choices. This is a pretty standard, just basic experiment though. And we're not going to try to break the bank here. We're going to give funky linearizations and weird analysis. That kind of comes in the C and D part. In experiment 2, students are asked to use a graph to determine the acceleration due to gravity g. The students attach a small sphere to a string attached to the ceiling. Before displacing the sphere a small angle, we vary the length L of the string and record the frequency of small angle oscillations. We can already tell this is not linear because we have this sort of decrease. It's not going to hit 0. We want to figure out how to linearize it. Okay. Well, this is clearly a pendulum, right? This is about as obvious as you can get that this is about pendulums. Now, we are given a kind of strange quantity. It's usually not the typical experiment to give you frequency. Usually we give you period. So the thing we do know is that the period of a pendulum is 2 pi times square root L over G. And we also know that this quantity frequency is the reciprocal of the period. So how do we linearize? Well, we know that our expression that relates frequency and length is just the reciprocal of the period. So frequency is going to be the reciprocal of 2 pi is 1 over 2 pi, and the reciprocal of L over G is G over L. So you could graph F versus 1 over square root L. I never graph square root relationships because it makes the slope math kind of ugly. So what I will always do, and this is my choice, I will always square roots away. So I can square both sides of this equation and get frequency squared is equal to 1 over 4 pi squared, right? Because 2 pi and 2 pi makes 4 pi, so pi squared. And then G over L just gets, we just free it from its square root prison and get G over L. So again, what did I do? I just squared both sides of this. That's a legal operation to get that. So now we have the relationship frequency squared is equal to, pull out everything that is not the other variable. So G is not the variable. Neither is 4 or pi squared, which means I'm just left with 1 over L that's factored out. So I can graph F squared on my y-axis, and I can graph 1 over L on my x-axis, which leaves my slope to be G over 4 pi squared. Now you could get sneaky and you could put this 4 pi squared on one of the sides to make G the answer. That's cool. I actually like doing that better. But most students like to put the simplest possible things in the box. So if you did the squared relationship, you get this. If you graphed F versus 1 over square root L, your slope would be square root G divided by the quantity 2 pi. You don't have to do this, but I did. I filled out my transformation variables in there. And we know right on cue, I'm going to say my usual phrase, we did some mining off camera to draw the best fit line. So let's show how I got my points. So first of all, C1 you get by selecting the linear relationship. So any transformation of variables equivalent to F squared and 1 over L works. The axes don't matter. So most of you might pick the F versus 1 over square root L. That might work. If you pick wrong and you do a nonlinear thing, that only locks you out of C1. Now, regardless, this is why I say just commit to your graph, even if it's totally wrong. C2, you get your axes plus the units. So you have to have consistent units, or none if it doesn't need units. And you also need a linear scale in your axes. So notice I count 1, 2, 3, 4, 5, 0.3, 0.6, 0.9, whatever. C3, nobody misses C3. C3 is just plotting the points to some reasonable level. Like if it looks like you just made up where the points go, you're not going to get the point unless if you trick us. But just plot whatever. If you commit to plotting the points, you get C3. And then C4 is a reasonable best fit line or curve. If you're like, okay, there's no way this is linear, I'm drawing a curve, you still get C4 because you probably missed C1. All right, calculate G from the best fit line. So I Desmosed this. I just punched the data into Desmos. I ran a linear regression, and I got y equals this equation. And if we go back to our work earlier, it is claimed that the slope of the best fit line is not G, but the slope of the best fit line is G divided by the quantity 4 pi squared. So we can say that the slope is equal to G divided by 4 pi squared, which means that G is equal to 4 pi squared times the slope, which is 4 pi squared times 0.243, which is equal to 9.59 meters per second squared. Which actually makes sense because physicists like to use the approximation that pi squared is equal to G, which is actually pretty close. So it makes sense that this number is about a quarter, and that times 4 is about 1, so should work out. Now how do we get points here? So you get D1 by identifying the correct relationship between the slope of your line or intercept and G. And then D2 is for the numeric value. So if you graph the wrong things, it's going to be very, very hard to get these points. And I was actually very mean with D, where it does have an acceptable range of values. I forget exactly what I picked, but I said if you just spawn in 9.8 with no work, no credit. Now, if your best fit slope allows you to get 9.8, that was different. But we're just saying you can't do absolutely nothing and spawn in 9.8 and get the correct answer. Realistically, I should have fudged my data to make it not close to 9.8, and it's not a great question designed by me, but we'll say reject 9.8 or 9.81 exactly if it looks like you just spawned it from the formula sheet. So that's a pretty standard lab question. I gave a non-trivial linearization here to kind of make us actually do it, but I tried to compensate by making the Hooke's law like a very P1 idea. Oh yeah, while we're talking about it, most of the mechanics exam could be done by P1 students. It's really only one of the 4 questions requires calculus today. Multiple choice, I put a lot more calc in there. All right. QQT is always my favorite. Finding ways to do it with and without math. A small satellite of mass little m is to be placed in circular orbit near a moon of mass big M. There's 2 possible circular orbits. We have the small orbit X and the large orbit Y. We want to compare the period of the satellite in each orbit without using equations. Then we want to solve for T. And then it's not actually consistency, then it's a little modification. So usually I'll ask about modification once and consistency once. So I'll try to swap those. Sometimes it's in the QQT, sometimes it's in the TBR. All right, compare the period T of the satellite in each orbit. Well, I certainly know a quantitative way of doing it. Now, if you have this in your brain, that's cool. If not, we can reason through it regardless. Now, if you have astronomy backgrounds, or if you did this during gravitation, there's actually a relationship called Kepler's third law. And people probably don't have Kepler's third law memorized by itself, but you might remember that it actually says the square of the period is proportional to the cube of the orbital radius. So this says that as orbital radius increases, so does the time required to complete an orbit. Now, I can't use that as my justification. In my rubric, I gave you one of the 2 justification points for Kepler 3, but this is totally not qualitative. This just spawns in. So I would say that we know for sure because of Kepler-3, the larger orbit should take more time. So how can we sort of almost like qualitatively produce a version of Kepler-3? Well, I always say start with the most basic physics fact that we can use to compare. And well, the orbit radius is bigger. That's literally the only change. So what does orbit radius change most directly? Well, that's going to be the gravitational force. So there's going to be a weaker gravitational force on the, oh boy, satellite. Yes, I had to look up to spell it. Weaker FG on satellite in orbit X, or sorry, no, orbit Y, since FG is proportional to 1 over r squared. That's not manipulating. Newton's gravitation law, I think that's pretty straightforward. So that's actually like the most basic fact is how you get the first justification point. So then for the second justification point, we need to say, okay, cool. Well, now the force is less. So what does the force unlock? Well, since the force is less, that's going to tell us something about centripetal force and centripetal acceleration. So this means we have a lower centripetal force. So there is a lower centripetal acceleration. Right? Because F equals ma. So if we have a lower force acting on the satellite in orbit Y, we must have a lower acceleration. And this acceleration isn't speeding us up or slowing it down. It's actually dictating sort of the rate at which we're curving around this circle. So now to bring it back in, we also know that centripetal acceleration is v squared over r, but that's not totally qualitative. So we would also reason that we have a lower acceleration and larger distance in orbit Y. So more time is required to complete one cycle, one orbit. So that's me trying to not use symbols for this. I know this is going to be a bit interesting to try to manipulate. So selection gets you 1 point. Newton's law of gravitation gets you a 2nd point. You just need to say the gravitational force weakens with distance. That's how you get A2. And now here was like my symbol-less approach to A3, where I said the force on the satellite is lower, which is what's keeping you in a circle. So your centripetal acceleration is lower. And now I tried not to skip to velocity, although we'll give you the point if you go to orbital velocity. So how do you get A3? Well, A3, I actually had you say 2 things. You either have to say that centripetal acceleration decreases or orbital speed decreases. But not only that, you also have to say that the distance traveled in orbit Y is larger than the distance traveled in orbit X. I know it seems obvious that the bigger orbit has a bigger circumference, but you do have to reason that, because what if I was moving slower but had to go less distance? That wouldn't necessarily mean it takes more time. So you did have to say, well, if I'm going at a lower speed / acceleration over a larger distance, I must definitely be taking more time. Now, a key way to see this sort of effect is if we wanted to use some more equations, you could say that centripetal acceleration can also be written as omega squared times r. This actually makes it a lot more clear that increasing the radius in this orbit is going to directly reduce the speed, because omega is more related to the rate that you're sort of sweeping out angle in the circle. So notice that if my acceleration decreases and my radius increases, well, the only way that could possibly happen is if the angular velocity decreases, right? Because I know the acceleration needs to decrease with distance, but distance is increasing. So that must mean that this other term omega must also be decreasing. So that's how you can also reason through it, is you have to realize that the centripetal acceleration is directly related to the rate that you're sort of turning around the circle. So responses that also use things like you're turning slower, like the rate of turning is slower, is sufficient to cover this bullet point. Anything about like the turning rate being lower also works out. But you do have to say that the distance of the orbit is larger as well. So that's kind of tricky. I think most people will get A1 and A2. But A3 is one of also those like elusive points on the test. Suppose the satellite is in circular orbit of radius r, derive an expression for the period. So this is basically, can you prove Kepler's third law? So what's going to be helpful here? Well, we know one thing that's going to be helpful is the force on our satellite is going to be gmm divided by r squared. But also we know that we're in a circle. And this means that Fg is supplying a centripetal force. So if the gravitational force is a centripetal force, remember centripetal isn't a type of force. It's really an adjective, it's not a noun. That means that we can just set gmm over r squared is supplying a centripetal force, and anytime anything is centripetal, we can set it equal to mv squared over r. Goodbye mass of the satellite. Remember, that does not matter, and it shouldn't, because our expression actually only has capital M and r. So goodbye. So that actually tells us if we reduce this, we get the relationship after the m's go away and one of the r's on the bottom go away. We get the relationship v squared equals gm over r. And you could keep it like this if you had the power of like foresight, like to know where you're going for this. But this seems to be useful, so let's just keep it. This would be the speed. And why is the speed helpful? Because we want the orbital period. So the orbital period, we also know that we're in circular orbit at a constant speed. So if we're in circular orbit, we know that we can use this fact, right? That distance traveled is equal to speed times time, right? So this means our distance traveled, which is 2 pi r, is going to equal the speed, square root gm over r, times the period t. And then we can substitute. So this would mean that t is equal to 2 pi r times the square root of r divided by gm. So if we do that, we get t is equal to 2 pi divided by square root gm times r to the 1 is r to the 2 halves, and r under a square root is r to the 1 half, so I get r to the 3 halves. So this is actually our answer. It said derive an expression for t, so this is our answer. And if you were a Kepler's third law enjoyer and you derived using Kepler 3, you'd get the familiar relationship. If we square both sides of this, we get t squared equals 4 pi squared over big G times big M times r cubed. Now, I actually did make an exception in this case. If you wrote that, I actually did award credit, I said, if you gave this form, because it doesn't affect the dependence at all. And it is a very common result. So if you wrote it using Kepler 3, that's acceptable. So how do you get your 3 points here? Multi-step about centripetal or Newton gravitation gets you B1. You get B2 by correctly figuring out something about the speed. And actually, I also gave you B2 if you said the speed is 2 pi r divided by the period. I also gave you a point if you said that. So any correct speed relationship gets you B2. And if you combine the speed relationships and solve it correctly, you get B3. So not the easiest QQT out there. There's some easy points and some hard points. And then for part C, instead of is it consistent, because I imagine a lot of you kind of knew it would be related because you knew Kepler-3 ahead of time. Like, is it consistent? Obviously, right? If I increase R, I increase T. So I thought that was a bit too easy to answer. So I gave you a modification. So suppose instead we have orbit Z, which is elliptical. And I give you the points of furthest approach, which is furthest approach is B, closest approach is A. We want to compare the satellite's speed at these points. All right. So what do we know? Well, this relates to another Kepler law. This would be Kepler's second law. That's how I teach this when I do astronomy, this fact. It's the equal areas and equal times law. So if you split your orbit into these little pizza slices, it says that if you wait the same time, the areas of these slices are guaranteed to be equal, even though their shapes definitely aren't. And the only way that that can happen is if you're going slow when you're far away, and if you're going fast when you're close. And I totally neglected that in my rubric. If you somehow cite Kepler's second law, you absolutely deserve point C2, by the way. So we'll keep a note of that. Because here's where Kepler's second law comes from. So one thing you have to realize is you can approach this with conservation of something. So this speed is definitely greater at A. There's a couple ways of approaching it. So the classic way of doing this problem is, notice that if I'm sort of in orbit somewhere, let's look at B, for example. If I'm in orbit somewhere, I'm going to be moving at some speed this way, and then my gravitational force is going to be this way. So when I do my torque, I'm getting no net torque exerted on the planet, or the satellite, sorry. So this is the sort of the standard solution. I would say that the torque caused by gravitation is 0. Sorry, I'll say the net torque is equal to 0. So this means conservation of angular momentum is conserved. So the fact that this angular momentum is conserved tells you thus, since R at point A is less than R at point B, this means VA must be larger than VB. So the quantity MVR remains constant. Because if I decrease my distance, I must increase my speed to compensate for that angular momentum being constant. There's another way of doing this that essentially you could say, or as you go from A to B, you're getting closer to the planet, which means UG increases. Which means if you get closer to the planet, your UG is going to decrease. So kinetic energy must increase. And why do I know potential energy decreases? Well, think about it like on Earth. If I drop a ball, the ball gets closer. If the ball gets closer to Earth, its potential energy decreases. Now, of course, you could just use this sort of formula and say that if your R gets smaller, you get a larger negative number, which is a decrease. This solution also works. So you need to justify it using conservation of something. It would be very hard to argue this based on forces alone. I'm trying to think of a solution to that. If you have a really convincing forces argument that doesn't conserve anything, let me know. I'd be interested in hearing that. With the correct argument, you could probably do it. trying to think of something about, like, we know that the pole is bigger at A. So if the pole is bigger at A, you'd get a larger centripetal acceleration, which would make you sweep out a smaller circle at that time. I'm trying to think through that. That'd be interesting, though. Let me know if you have a good explanation with forces. My intention is that you pick conservation of angular momentum / Kepler 2, or you pick conservation of energy that shows the gravitational and kinetic sort of trading. Yeah, I thought this was a pretty nice sort of exam. Maybe 90% is a bit too tall of a task to ask for my fives here, but I thought there's a lot of ways to show success here. We might not get a clean sweep on everything, but these are some nice problems, I think. These are some nice little free responses. Now, of course, you can just check my description on what I end up thinking the cut scores should be for the like total. But yeah, this is a nice little practice exam. Tests a lot of nice skills and at least gets you used to the format, because the format is everything for this test, is understanding what types of things we ask. And this actually really did a good job of going through lots of the course. Alrighty, let me know if we have any questions.